Okay, good morning. Welcome to the last day of Akamai Edge 2014. I hope you've all been having a great time so far here. My name's Eric Nygren. I'm a chief architect in Akamai's platform engineering organization. And I've been at Akamai for around 15 years now. And kind of over those 15 years I've been at Akamai, even starting back in the beginning, IPv6 was always been this one of these things where it's like, yeah, that's going to be here any day now. And it was never there. And then 5 years later, it'll be here any day now, and then it was not here. But now, actually, it is here. And I think one of the things, this is actually coming as a big surprise to a lot of people because there's been such big final adoption of IPv6 as a lot of the groundwork laid over the past decade and a half has started to pay off. I'm going to talk about this. So first of all, I'm going to give you some background about IPv6, telling you a little bit about what it is, what the motivations for it are. I'll be talking about why is it taking so long? Why has it taken us since some of the work started in 1996 until today to even be at a point where it's really starting to pick up steam? I'm going to talk about the adoption landscape, where IPv6 is starting to show up and where it isn't. It's actually different than what people were expecting it would be like a few years ago. I'll talk a little bit about some pitfalls of IPv6, things you should watch out for even today, even if you're not actually starting to take advantage of it yet. I'll talk very briefly about what Akamai is doing around IPv6 and give you some things you can take away to start thinking about to make sure that you're not caught completely off guard. So on the background side, the motivation for IPv6, all else said and done, really comes down to the fact that the Internet's running out of IPv4 addresses. And the IP address being the thing that you use to communicate on the Internet, this is fairly problematic, to put it lightly. There are only, because IPv4 addresses are a 32-bit value, there are only 4 billion possible IPv4 addresses. And some of those are reserved for multicast and local hosts and private addresses. And you need these across client servers, SSL virtual IPs, and so on. And if you start looking at where IPv4 usage is, the IP addresses are handed out by network registrars. There's one for each region that has these pools of IPv4 addresses to give out. And if you look at where Asia and Europe are, they actually got to the very last bits of their pools in 2011 and 2012, where they went into a conservation mode and are now just trickling out the last little bits of them. If you look at where South America and North America are, South America actually exhausted their pool earlier this year, and ARIN in North America is looking like it's going to run out at the beginning of next year. And unlike Asia and Europe, the North American registry isn't even leaving this big conservation pool of stuff to start handing out. They're just going to let it go all the way down. And what this means is that IPv4 is going to start becoming much more of a constrained resource. Today, it's one of those, if you can show need, you can get them. Soon it's going to be you have to show need and then go find someone you can go and use some sort of market economy to go buy those IPv4 addresses from. So you want to build out some new big data center with 10,000 servers that you all want to be publicly addressable, and you need to go find IPv4 addresses from there, and they're not going to be free anymore. And this is really going to change a lot of things in how the Internet runs. So the ugly old... Yeah, and I'll take some questions more at the end, but is it...
I didn't know what the y-axis was.
Oh, the y-axis there is the number of /8 address pools. So each /8 address pool is 24 million addresses. So they're 16 million addresses. So they are once they get to that one line, that's only 1 /8 that's left. The ugly alternative to IPv6 is something called NAT, or Network Address Translation, as well as its big cousin, carrier-grade NAT, which is kind of a label slapped onto it saying we're going to do this for tens of thousands of individual IPv4 addresses behind a single, or tens of thousands of users behind single IPv4 addresses. And what this is going to mean is as it starts to get picked up, is more and more little bubbles of the internet that are actually disconnected from each other. Because these little private IP bubble spaces behind NATs aren't actually going to be able to talk to each other. If you have a user behind one NAT and a user behind another NAT, there's no direct communication. If you want to talk between each other, you need to play weird games to try and trick the NATs into letting you talk to each other, or you need to talk to relay servers out in the internet. And this is not the way we want an open internet to keep evolving. It isn't going to keep scaling. And if you look at the number of IPv4 addresses, with only 4 billion addresses, and as you've been seeing in all these slides this week talking about the 7 billion people in the world and the 10 billion devices that are out there right now and the 50 billion devices that will be there in a few years with Internet of Things, it's clear that there's just not enough IPv4 address space to go around and meet the needs of the internet. So this is where IPv6 comes in. It's 128 bits. You have 10 to the 38 possible addresses, which is enough to give 50 million addresses to every bacteria on Earth. So, and even if the current allocations of it aren't actually being used in ways that are somewhat sparse to make routing more efficient on the internet, we're only using a tiny fraction of the IPv6 address space for the next foreseeable future, so that if we screw it up this time, we have a few more times with an IPv6 to try again with totally new addressing schemes, have things still all work and interoperate. So one of the things that's hardest to understand about IPv6 is how it relates over to IPv4. And I think a logical way I think of it is you can almost think of them as two separate internets. You have the IPv4 internet and you have the IPv6 internet. And many hosts and devices are connected to both of these internets at the same time. And a device that's connected to, or a service that's connected to both the IPv4 internet and the IPv6 internet is referred to as being dual stacked, because it has an IPv4 stack and an IPv6 stack. Similarly, if you have some service that's available, or website or content that's available to both IPv6 and IPv4, it's also referred to as dual stacked. And those dual stacked devices have both IPv4 and IPv6 addresses. And if you have a device that's on the IPv6 internet, it can only connect directly to things that are on the IPv6 internet, and same with the IPv4 can only connect directly to things on IPv4 unless you use some sort of NAT technology. For example, there's a NAT technology called NAT 6-4 that allows devices with only an IPv6 address to go and make connections outbound to legacy IPv4 services. And I'll talk a little more about that later. But some of those NAT technologies also have many of the same problems that inherent with carrier-grade NAT. So in that NAT 6.4 world, you have the ability for an IPv6 end user to go through a NAT 6.4 gateway, talk to an IPv4 service, but similarly within the NAT 4.4, or IPv4 to IPv4 NAT world, those NAT servers can be bottlenecks and congestion points where they can either run out of outgoing ports, they can be overloaded because there wasn't enough capacity on them. So there's a lot, and you lose all the visibility that you might need for client reputation to the machines behind them. So we really want to get to a world where there's as little NAT as possible. So what's taking so long? Why is it that we started out in 1996 working on IPv6, and now it's 2014, and we're still in this case where you ask a lot of people, and they're like, oh, what's IPv6? I've been hearing about that forever. It's not anywhere. And a lot of it, there's a lot of stuff that needed to do, because we're really taking the center of the internet that everything uses and overhauling and replacing it with a whole new thing. So you had to get OS support in place, client software support, infrastructure and backbone network router support, content to be available, end-user connectivity brought up, end-user customer premise equipment devices like home routers and gateways supporting IPv6. There's all this stuff that needed to get done. And this is the stuff that people have been working on for the past 15, 20 years. So the OS support, client software support, infrastructure backbone support, a lot of that is there now. It's implemented in the 2000s. There are still little issues that remain. There are a lot of kind of gotchas that are being found as we're doing wide-scale deployments, assumptions that were made in 15 years ago about how networks would look that don't necessarily hold true. So there's still being tweaks made here and there. But a lot of that groundwork is laid. And even the content availability, end-user connectivity, and device support is really starting to move forwards. And it used to be that we were stuck in this chicken and egg bubble of no one who had content wanted to make it available over IPv6 because there were no end users on IPv6, and no one wanted to bother putting end users on IPv6 because there was no content out there for them to get access to. And back in 2011 and 2012, the Internet Society put together a World IPv6 Day, followed by a year later by World IPv6 Launch, to really try and break that chicken and egg. And so far, it's actually been working. And now we're turning this crank of more content, meaning more IPv6 traffic, meaning networks are more willing to put roll out IPv6 to their end users, which means there's more users out there, which means that content providers are more motivated to get more content. And this cycle will hopefully keep going and not stall out. And that kind of leads you into where is that cycle now? Where is IPv6 adoption? If you look at IPv6 traffic on the Akamai network since that 2011 point, a few years ago when we had World IPv6 Day, back then Akamai was seeing about 280,000 IPv6 addresses over the course of a day. And we were seeing about 8.3 million IPv6 requests per day, which is still a bunch of requests, but still fairly small. Now in September 2014, we're seeing 225 million IPv6 addresses per day. In fact, over the course of a week, we see over 1.5 billion IPv6 addresses reaching our platform. Some of that's due to clients a lot of that's due to clients changing their IPv6 address on a day-to-day basis due to something called privacy addressing. So it makes it kind of hard to measure how many IPv6 end users are there out there. But right now, it's probably somewhere in that 200 to 300 million users with IPv6 connectivity range. And we're now seeing about 38 billion IPv6 requests per day against the Akamai platform. This graph up on top is showing how many billions of IPv6 addresses, actually how many billions of IPv6 requests per day Akamai is serving, growing since 2012 to the present. It's just going up and up and up due to more content, more on Akamai being dual stacked, more client networks having IPv6 connectivity, and better support out there.
Can you give a sense of percentage-wise, like 38 billion requests a day? Is it a trillion of IPv4? What is it?
That's what I'm going to get into now. So, or get into this slide after this one. So on the client device support out there, most of them, pretty much everything modern operating system-wise that you're running on your laptop, your smartphone, your desktop computer, your server has IPv6 support, whether it's Mac OS, Windows, Android, iOS, Windows Phone, BlackBerry, even a bunch of set-top boxes and televisions all have IPv6 support in them now. And pretty much all of those have it turned on by default when there's IPv6 connectivity available. And many of those, the client softwares also implemented something called happy eyeballs, which means that if they try IPv6 and it doesn't work, they have some sort of fast failback mechanism to IPv4 to avoid resulting in end-user connectivity impacts. And actually, some of those happy eyeballs implementations have the added benefit that clients will, such as Safari on OS X, will actually try both IPv4 and IPv6 roughly around the same time and use whichever one is faster. And that means you actually have two choices to get out there, and you can actually get some performance benefits from that. And on the content side, it is no longer the case that there's no content around there. If you look at a lot of the big major websites that you go to on a day-to-day basis, whether it's Facebook or Yahoo or Comcast and MSNBC properties or Netflix, a lot of, and this is a small, tiny subset of them, all of those have been making IPv6 connectivity available by default for their websites and web properties. On Akamai now today, we have over 5,000 host names live dual stacked for over 150 customers. And as well, and included in that are thousands of US government websites. Going to the percentage question that was just asked, the way I'm going to be measuring percentage for the next few slides is talking about the number of IPv6 requests we see to dual-stacked websites, or content that's available over IPv6, relative to the overall number of requests coming to that. So it's kind of trying to do an apples and apples comparison for if you have some content that's available over both IPv4 and IPv6, what percentage of users show up and try to get that content over IPv6. And this graph here is what the United States has looked like for that since 2011. If you look back just at the end of 2012, beginning of 2013, that was just barely over 2%. Today, we're getting up close to 9.6, 9.8% range. And actually, this is measuring by requests per day. If you measure this by the number of bytes transferred, those numbers are even higher. The US, we're actually serving around 12% of the bytes to dual-stacked sites over IPv6 today. And if you look at other countries, it's not just the United States that's been seeing this growth. The United States, and these graphs here are just over the past 15 months for some of the leading countries in terms of how much IPv6 traffic we serve to them. The United States over the past 15 months has gone from being less than 5% up to 9.7%. Germany is over 10% now. Belgium is around 25%. France has been stable at about 5%. Japan has risen up from around 2-ish% to almost 4%. Even Peru is actually, and the latest numbers that I ran earlier this week was getting close to 10%. Greece and Norway also have been shooting up over the past few months and are also both close to 5% now. And what drives this is that it's actually a function of the underlying networks within those countries that are making connectivity available to their end users. I'll talk a little bit about that in a second. So if you look at the networks that are out there, this is just a small, tiny set of them. There are Akamai has IPv6 connectivity in over 450 of our network partners today. These are just some of the ones we see lots of IPv6 traffic from. And the growth in any given country is a function of which network providers in that country are starting to roll out IPv6 to their end users, and how do those compose together. So the whole story of what that growth looks like is take a bunch of network providers, start composing them all together, but then also for the country level, it's also what is the traffic ratios and content ratios within country. So it may be that some network provider in a country rolls out to a subset of their user base, like all of their users using a certain ADSL service. And then the country level percentage may be is a function then of how many of those ADSL users are there relative to all the other users in their country. So if that kind of proportion goes down a little bit, then the country number may slip until they start rolling it out to some other fraction of their end users, or until other networks within that country roll it out. Some of these are also then tied to customer premise equipment within customer networks. So for example, the top on this list, Comcast, which by requests per second is getting close to 20%, but by bytes is well over 25%. There, the thing you start running into is it's Windows XP devices on their network that don't support IPv6 or kind of holding things back. Old home routers or home gateways people have that don't support IPv6 are holding things back. But Comcast actually has IPv6 rolled out across all of their network POPs. Verizon Wireless is actually over half, at 55% of their users have IPv6 connectivity now. All the new phones that they're rolling out, whether it's new Android devices, new iOS devices, all come with IPv6 enabled on them. So if you have one of those phones in your pocket today, you have IPv6 connectivity, and you're probably using it every day as you're browsing sites like Facebook and Google and others. Those connections between you and those servers are going over IPv6, and you don't even know it. AT&T has also been rolling out IPv6 in their network. Time Warner Cable's been rolling it out in the US. Deutsche Telekom, Liberty Global, and Kabel have been rolling it out in Germany. KDDI and a number of others in Japan have been rolling out IPv6. Proxads in France. Telefonica Peru is actually the network that's been driving the IPv6 adoption in Peru, and why Peru is so high there in the country stats. T-Mobile US, 15 months ago, had almost no IPv6 on their network, and since then, all the new Android phones they're shipping have been actually shipping in a configuration mode where they're actually IPv6 only, where they don't even give an IPv4 address to those phones. And when you go out to make connections to the outside world, your IPv4 traffic is actually tunneled over IPv6 and goes out of NAT. And that's up to about a quarter of the devices a quarter of the traffic on their network to dual stacked sites is in that state. And you start seeing other countries that are in this mode. Like, for example, Brutalavu in Belgium, they went from, over the course of about 2 months, they went from some fairly small number of, or some like 20% to 54% rollout. And you start seeing some of these networks where they've been doing trials for months and months and months or years, and now it's kind of like, okay, everything seems to work, we flip the switch, and suddenly the country or the network jumps way up in IPv6 usage. One of the areas that I kind of alluded to that's leading this adoption trend is home broadband. This is the Comcast, the AT&Ts and such of the world. A case example of this is Comcast, which is the biggest IPv6 network in the world right now from an end user perspective. And quoting a blog site on their a blog post on their website, you can go read. They now have 100% of their backbone connectivity has IPv6 dual stack. They're getting over 1 terabit per second of internet-facing native IPv6 traffic coming into their network. And their Xfinity X1 set-top box that they've been rolling out to their end users and is their platform of the future for delivering content to home televisions, is planning to move to have IPv6 only support for it sometime in the next year or two. Well, they're actually going to be reclaiming all the IPv4 addresses back off those boxes. They don't need to bother with it, and then set up some mechanism for that legacy IPv4 content. But that means that as a content provider, if you want a good high performance, high bandwidth video or other media content to that set-top box, if that content's not available over IPv6, you may not have the best experience as compared to content that is available over IPv6. They've been doing the same with their voice. Their voice over cable services are now moving to use IPv6 under the hood. So those little modems you might have in your house for doing voice they don't have to have private IPv4 addresses to manage anymore there. Another area where we've seen a lot of adoption is on the mobile side. This is where one thing that the carriers have advantage of here is that they control the handsets in many places, and there is nothing between that handset and them. So if they get IPv6 support working in the handset, and they have IPv6 support working on their end, they can do things like roll out IPv6 only handsets in a way that allows them to run a lot of their network without needing to keep growing their usage of IPv4. And some of the mobile providers before this were running into the problem that they'd actually run out of private IPv4 space within their network to hand out to users. They started to have multiple bubbles of the same IPv4 addresses in different portions of their network. So you might have a user with one IPv4 address in Chicago and another user with the exact same IPv4 address over in Dallas, and that was becoming a real pain to manage. And this makes life much easier. And T-Mobile US and Verizon Wireless really led the way here in getting a lot of the technology working, both in the handsets and in some of the network equipment, and a number of other networks like Orange Poland and E in the UK and Telenor and SK Telecom have all either announced or in progress of taking advantage of that and starting to roll out IPv6 as well. Governments have also been a big driver in IPv6 adoption. In the United States, there's the U.S. government purchasing requirements will put in place in 2010 saying that things you're selling to the U.S. government have to support IPv6. And the Office of Management of Budget actually put out a mandate saying that by September 2012, public-facing websites must be available over IPv6. And kind of in the lead up to that, Akamai worked with all of our public sector and U.S. government customers to go make that happen for the ones that we were serving. And then there are additional mandates that the U.S. government, OMB, is starting to roll out. One of them hit earlier this year. There's another one. They're trying to figure out what should be the next one to start driving more and more IPv6 adoption. And the U.S. government's not alone here. There's a lot of European governments and Asian governments that are also starting to pick up similar sorts of mandates and starting to look at, oh, if we're buying stuff from some company, does all of their software support IPv6? And does all of their hardware support IPv6? And do the services support IPv6? And this is going to start really mattering more and more to businesses who, if you want to sell a printer into the U.S. government, and that printer wants to get firmware updates over the internet, if that printer can't get firmware updates over IPv6, then there's a good chance that at some point, if you're talking to the right purchasing person, they'll say, sorry, you can't sell that printer to the U.S. government, or if it's some European government, they'll say, we can't buy that from you because you need to support IPv6 due to our purchasing requirements. And that's been helping drive adoption as well. For more of these statistics, there's a number of different sites. The rolling out in a few weeks the State of the Internet reports that David Belson's been publishing on a quarterly basis containing IPv6 statistics. We're going to have some very up-to-date ones that are going to be updated on a regular basis that are going to be going live soon. So keep an eye out there, and some of those stats will be showing up at stateoftheinternet.com. Now, IPv6 isn't all rosy and glossy and alpacas. There are also a bunch of pitfalls out there to watch out for. One of the ones is, as we keep hearing about over and over again on all other topics, is security. And there is malware out there supporting IPv6. Even back in 2011, we started having websites start getting dual stacked on Akamai. We started seeing infected hosts following the Quad A DNS records and starting to attack the Akamai platform over IPv6. And there's more and more of this because with large number of hosts and end users around the world having IPv6 connectivity, any infected machine out there where the malware is using the local network stack to make outbound connections will probably just be able to make those outbound connections over IPv6 as well. So on the Akamai side, we're constantly blocking ongoing probes and attacks over IPv6, but you definitely need to make sure that any firewalls or other equipment you have out there supports IPv6 at the same level that it supports IPv4, because otherwise there's exposure there. Another pitfall is that not everything that claims to support IPv6 supports it fully. In some cases, there are vendors who make some device and they treat IPv6 as this vendor checkbox. They'll say, yeah, we support IPv6. And that meant that they went and talked to some engineer, and the engineer said, yeah, we support it. And it's kind of like some little tiny thing that's not actually tested and barely works. That's happening less and less often, but it's certainly something that's still out there. Also, some of the IPv6 connectivity is still spotty. We're rolling out a whole new internet. Sometimes this whole new internet is actually a lot faster than the IPv4 internet. And there are a bunch of features that are going to be available there that are going to make things better over time. But there's still cases where pockets of the IPv6 internet can't talk to other pockets of the IPv6 internet. And Akamai's Network Operations Center is constantly finding these between through our network monitoring probes, and we're reaching out to some of those network operators and saying, hey, did you know that IPv6 is broken in this part of the internet, and working to try and get the IPv6 internet working much more reliably and getting it cleaned up. The other thing to watch out for is that systems that are directly handling IP addresses may need to have some updates to deal with it. And across the board in general, the hope is that the IPv6 transition is really smooth and transparent to end users and software as much as possible. But at some point, if your software is dealing with an IP address, you're going to start needing to think about IPv6. For example, if you go and start sticking, if you have authentication cookies that you stick an IP address into, then and that comes to one server over IPv4 if a client comes to one server over IPv4, that cookie gets set with the IPv4 address, and then this client goes to another server over IPv6, passes that along. That cookie is not going to match up. Even with carrier-grade NATs now on the IPv4 side, they're starting to use multiple IPv4 addresses as exit points. So cookie-based IP locking schemes are actually starting to break down just in general and are going to start becoming something that don't really work anymore on the internet, regardless of IPv6. Another thing that you have to watch out for is cases where you're communicating taking IP addresses and storing them someplace. For example, if you're getting a true client IP or X-forwarded-for header or log field being delivered by Akamai to you, and the client's connected over IPv6, you need to make sure that anything handling or processing that address can handle IPv6 addresses as well. If you have a 15-character database field that you store IP addresses in when a user clicks checkout on your e-commerce site, which works just fine for an IPv4 address, and you now try to stick a 30-character IPv6 address into that, you're going to get some exception thrown by the database, and the user's going to get some, sorry, I can't check out due to java.awt blah, 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 blah exception, and the user's kind of like, So there's some of these that are also that you have to watch out for as part of making content available over IPv6. On the flip side, there's the risks of getting behind on IPv6. If you not providing IPv6 immediately today the internet's not going to immediately break for you, but as more things like IPv6 only set-top boxes start appearing out in the world, you're going to start, or more IPv6 only handsets that use NAT for their IPv4 connectivity, your IPv6 users are having IPv6 content available on your site, or IPv6 media available, means that users are going to get a better experience than if that wasn't the case. And this is going to get more and more and more extreme over time as the crunch of IPv4 exhaustion starts hitting more and more networks, and as those networks grow and try to keep scaling up. You also, in the IPv4 world, as more carrier-grade NAT keeps getting used, are going to start losing visibility into end users out there. So if you have a system that's trying to do IP reputation or doing geolocation or blocking abusive users by IP address, and the users in some countries start coming to you through a carrier-grade NAT that has tens of thousands of users behind it, which is already happening in a lot of places, you're going to start losing the ability to do more and more of that. And IPv6 helps give you that visibility into all of the IP addresses of the end users out there. And then, as I mentioned before, you could also run into compliance issues trying to sell stuff to the US government and other governments around the world. And finally, IPv6 is one of those things. I think someone put it to me once as it's kind of like eating your vegetables. It's something that you don't really get a lot of credit for doing it. You can't go put out some big press release saying you did it. But it's an important part of showing technology leadership and helping the internet move forwards and keep scaling to unlock a lot of the things we want to get out of the future internet. So to talk very briefly about Akamai and where we are with IPv6, we're really committed to helping the internet have a smooth transition for IPv6. We're trying to help our customers make it easy to make content available over IPv6 while improving or maintaining performance and reliability. Today, we also even provide a IPv6 to IPv4 translation service, where if you have content available on your origin over only IPv4, we can go make that content available to your end users over IPv6 as well. And soon, probably sometime next year, we'll have actually that should say IPv4 to IPv6 translation service, where we'll be able to help. If you want to build out IPv6 only infrastructure and not have to worry about having IPv4 addresses on your servers, we'll be able to help you still deliver that content out to IPv4 end users. And many to most Akamai solutions and products have robust support for IPv6 today. There are still little limitations and feature gaps that we're working through in corner cases, and it's still opt-in, but at some point dual stack, probably initially for new content and then available for all content, is going to have to become dual stack as the internet continues to make this transition. We now have IPv6 configured and live in over 81 countries around the world, 400 cities, 490 networks, 1,200 server locations. So it's no longer just, IPv6 on Akamai isn't just we deployed in a few places, we're done. It's we're deploying this in all the network partners around the world that have IPv6 connectivity that they're willing to give us. And as I mentioned, we can make content available to dual stacked end users over both IPv4 and IPv6, even if your origin only supports IPv4. So what can you do? If after listening to this, you're saying like, oh, I guess I need to actually start paying attention to IPv6, probably the first thing to do is to try to put together a roadmap and start thinking about what are the things that are most important to you. For example, at Akamai, we haven't been taking a let's do everything at once approach because there's just too much to do it all at once. For our business, the most important thing was to make it so that our customers could deliver IPv6 content to their end users. And so that was where we started focusing on first. There's a lot of other stuff on the back end that we needed to make IPv6 ready and have been doing over the past number of years to get there, but your business's needs may be different, and so you want to find the key areas and target them. You also want to be thinking about where does IPv6 support fall into your purchasing requirements. If you're buying a bunch of new gear that you're going to be stuck with for the next 5-10 years, you don't want to be buying gear that you're going to be stuck with that doesn't support IPv6, because then 3 years out if you start saying, oh, well, I need to actually really leverage IPv6 in this environment, if that gear doesn't support it, you might have to go replace it. So start thinking about that now, especially when you're buying new security products, networking gear, and cloud provider services. You can also start looking at what content do you want to make available over IPv6. Some people start small, picking some little like a portion of a brochureware site or a blog site and make that available over IPv6, start getting some exposure and experience. That sort of thing, if you're on Akamai, is easy and straightforward. You can just talk to your account rep, or even in Property Manager now, when you're provisioning a new site, there's a little click box that currently the radio button says IPv4. And if you select IPv4 plus IPv6, that content is available over IPv6. And you can also support IPv6 when you're starting to build new systems and look at how you can leverage IPv6 to make things more simple. For example, there are some large content providers out there now who, as they're building out new data centers, are actually building out those new data centers IPv6 only. And it's a bunch of work, but it actually has flattened out a lot of their architecture and made life easier for them. And all they need to have for IPv4 address is a few things on the outside, but everything else within their corporate environments are IPv6. So on that, I'll leave you on kind of the traffic growth slide for here. I guess I have time for like one question. Any? Okay. So the question was what does support look like across Akamai products? And many to most of them support it. So for example, Kona Site Defender and the Kona functionalities fully support IPv6. Ion, Alta, Site Accelerator, site delivery, object delivery, downloads. There's like a long list of them that support it. So talk to your services folks, and they can help you with. They can help you find out exactly for which product and features you're using, kind of where we are in terms of IPv6 support today. And for the ones where there are some feature gaps, don't worry, those will get closed soon.
A lot of companies want, like private IP address space within their company, right? And then they'll have a public out-facing IP address. When you think about it, if Akamai goes down the approach for some companies, caught my interest the other day was the concept of going dark.
Mm-hmm.
You know, where Akamai would you wouldn't even see that company's website. It would all go through Akamai and be dark.
Mm-hmm.
Any comments on that as far as what that might do? Because it gets the company out of the whole issue of this sort of thing and some of the security items.
Right. So the quick answer, and looks like people are starting to show up for the next talk, is that one of the problems with going dark with IPv4 is there's so little private IPv4 space, and there's a lot of complexity around how do you go and manage that if you especially start having multiple services. So IPv6 actually makes it easier to do some of that. You can pick some bubble of, like, there's a space called ULA space, and create a private set of IPv6 space to use that within some environment. Or on the internet side, you can create pick some portion of your IPv6 address space and start putting more and more controls over that. But I'm happy to talk and take more questions kind of offline now. Thanks, everyone.